So, quick reminder, all these videos are up on YouTube, so we can figure out obviously edited so this goof didn't happen. The test is due on Wednesday. Due on Wednesday. By the end of the day, you can get it to me in various different ways. What I was trying to show you is you can turn it in person, you could slip it under my door, you can email it to me, you can email it as a PDF, as a Word document, you could take pictures of it and email me to me, or you could upload it onto Google Classroom under the exam file. All those are valid ways to get it to me. You're allowed to work together, but please note, as you're working together, make sure you have the same version of the test, and make sure you don't simply copy. If there's an essay question, make sure you're answering your own. Make sure you put it in your own words. I penalized a couple people in my 112 course for just directly copying. So, word it in your own words, and you should be good. Now, let's see. The other thing I mentioned, it was that don't forget in the lab, there is online labs. There should be one coming due, but it's only it's a rough due date. You could turn it in at any time. I'm just saying you should probably be working on it. You could do any of the available online labs. They may take you a little bit of time, or they may take you only 10, 15 minutes. Figure out which one you want to do. Let me know what materials you need. I can get it to you. You can do that. Okay, with that in mind, we'll go ahead and get started with the notes. So, quick reminder. We were previously talking about quantum theory. We're talking about the types of orbitals, where the energies are in an electron cloud. We broke it down into there are principal energy levels, which is like what layer of this Russian nesting doll do we have? The lower the number, the closer to the nucleus. So we had layer 1, principal energy level 1. Then we had principal energy level 2, principal energy level 3, and so on. Let's go back to one of the images I drew last Friday. Pulling up there. When we looked at that, we had various different energy levels. We go each one bigger than the other, going its way out. And then we started talking Friday about the various orbitals, the various different orbitals, sub-levels within the energy level. Like we had, when level 1, we only had the s orbital, the s being a shell that looks just like a hollow ball. Then in level 2, we had a 2s, but we also had 3 different orbitals, which were p. In this case, a px, a py, and a pz that went along with the 2s. And if we went to 3, we would have a 3s, we would have 3 3p's, and we would actually have a 3d, which we'll get to. But how did those look? The s's were just a straight up shell. The p's were like a double lobed orbital, which kind of looked like a bow tie without that center. Or you could call it a dumbbell or a figure 8. Now the d orbitals looked like clover leaves. So it's like 2 p orbitals put together for the most part. There's 5 different ones. And there's one of them that looks really weird, like a wheel and axle. And there's the wheel and axle one. And then f orbitals, which is the last type, there's 7 different possibilities. And we really won't try to deal with them too much because they're a hot mess. So they look more or less like you double up some of the d orbitals. Like this one has, instead of 4 lobes, that has 8. This one has 6, and that one is like a doubling up of that z squared. Now, typically the s orbitals are going to deal with, as we'll see, column 1 and 2. The p orbitals will deal with columns, like 13, 14, 15, 16, 17, 18, also known as 3a, 4a, 5a, 6a, 7a, 8a. The d orbitals will be with our transition metals, and the f orbitals will be with our lanthanides and actinides. Now, as I said, as the principal energy level increases, more subshells become available. So there's a weird terminology here where L will range anywhere from 0 to n-1, where L of 0 is S, L of 1 is P, L of 2 is D, L of 3 is F. So meaning that when energy level is 1, we only have, it ranges from 0 to 0. So it's only 0. So when we have energy level 1, we have only one possibility. When we have energy level 2, it ranges anywhere from 0 to 1, or S and P. When we have energy level 3, we have 3 possibilities. When energy level 4, we have 4 possibilities. Now, each of these subshells will see an increase in energy. So if you compare that S to a P, to a D, and to an F, the S and P, the S is going to be lower in energy than the P. The P is going to be lower energy than the D. The D is going to be lower energy than the F. And so, like you can see right here, at least very vaguely, that so if I took the S and the P and split them into the actual energy designation, you see S, and then P jumps up. So it's below the 3. 3P, and here's actually 3D. 4S, 4P, and you can keep going up. 4D, way up here, 4F. Now, you'll notice here that the 3D here is higher in energy than the 4S. The 3D orbitals are higher in energy than the 4S. And if we're going to be filling in energy, we're going to fill from the bottom up. Fill electrons from the bottom up, and this is going to result in some weird stuff. But this 3D orbital being so high in energy is going to be responsible for a lot of properties of row 3 elements. Why row 3 elements do things that row 2 elements could not, because it has essentially this high energy attic that is empty. You're like, oh crap, I got a bunch of electrons I need to store somewhere. Where am I going to put them? I'm going to put in this attic up here. I just shove it upstairs in the attic until I need it. So you have this big empty space that I can put electrons that is not available on row 2. Now, as you notice, there's 3 blanks for P. There's 1 blank for S. There's 3 orbitals for P. There's 1 orbital for S. These 3P are all at the same energy place. These are called degenerate orbitals. Degenerate means same. So degenerate energy, and so these are all of the same energy. All of the d orbitals are at the same energy. So there's no designation whether I put an electron here or there or there. And these guys, the number of orbitals ranges from m sub L, where it ranges from negative L to positive L in integer values, which explains why S of 0 ranges from 0 to 0. There's only one possibility. P ranges from negative 1, which is 1, ranges from negative 1, 0 to 1. There's 3 possibilities. Now, I'm not really going to call you on this during a test, but there's maybe a couple homework problems that ask about the weird designation, which is why I'm kind of going through this. But so m sub L, which is our magnetic quantum number, which has to do with whether it's a px, a py, a pz, or dxy or dyz. It's like looking at how many designations there are. Now, as we put electrons in here, the first thing we will do is we'll put electrons in here, and then we'll try to label this in a way that tells us how many electrons do we have in each orbital. So looking at nitrogen, nitrogen is element number 7. It's the 5th over on row 2. It has 7 electrons. So we're going to put up and down electrons with half arrows designating an electron. Where 7 electrons, we put 1, 2 in the s, 3, 4 in the 2s, 5, 6, 7, so 3 into the 2p. You'll notice as I put them in, I see an up and a down in each box. As I put them into the p, as I would have put them into the p, I put 1 up, 2 up, 3 up. I'm going to put all of them in the up position before I start pairing them, and we'll get to why that is in a minute. Now, when I go to labeling this, and I'll talk about this more in another slide, this is designated as 1s2. So 1s with the 2 superscript. The 2 tells me how many electrons are in the s. 2s, 2, and 2p, 3. So 1s2, 2s2, 2p3 tells me where all those electrons are at within the nitrogen orbitals. Chlorine, which is like number, I'd like to say 17. There's 17 electrons to place. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And I put 13, 14, 15, 16, 17. I put the last 5 into this 3p. So this becomes 1s2, 2s2, 2p6, 3s2, 3p5. And if I went all the way to cobalt instead of being at 17 electrons, it would be 18, 19, 20. 1, 2, 2, 3, 4, 5, 27, I'd like to say. But you could just start from where we were at. We're adding another 10 electrons. So from 17, fill that up, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. That one goes 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3p7. I'm just literally saying what energy level, how many electrons. And if you have this drawn for you, this should be the easiest thing in the world. We just fill it in based on what is its atomic number. So these electrons are arranged in the atom. We're building the atom in the ground state. This is the lowest energy state for the atom, based on 3 basic rules. One is the Aufbau principle, German word for the building up, where the electrons are put into the atom from the lowest energy to the highest energy. So we're going to put in 1s before we fill 2s. We're going to put in 2s before we fill in 2p. It's the same way as you're filling up a jar with colored sand to make a pretty like sand design, sand art. The sand that you pour in first is going to go sink to the lowest point. The electrons you put in the atom first are going to go to the lowest point. Hund's rule, that all orbitals of the same subshell will be filled prior to the electrons being paired. Basically, this one says, when I have like 3 orbital choices, all of the same energy, I'd rather put electrons as far away from each other as possible before I pair them up. Because electrons are negative. Put 2 negative charges together, it's not too easy. I'd rather keep them far away. I'd rather socially distance these electrons before I start pairing them up. Now, the Pauli exclusion principle, this is where all that naming stuff and the rules come in. Each orbital can only hold 2 electrons, and for this to happen, they must be opposite spin. The exact Pauli exclusion principle actually states that no 2 electrons can have the exact same designation. No 2 electrons can have that exact same designation, meaning if you have electron in the s and it's up, it cannot be one up electron in the 1s and another up electron being the 1s. It would have to be in the 2s. If I have an up electron in the 2p, it must be in either 2px or 2py or 2pz. I can't have 2 of them up in the 2x. And if I have 2 electrons within an orbital, one must be up and one must be down, because that's going to give it a different designation. Basically, no 2 electrons can have the exact same descriptive numbers. But okay, to practice. Going to practice, we have silicon, which is 14 electrons, calcium, which is 20 electrons, and bromine, which is 35. I can use the same darn thing for this. I'm going to go to the doc cam. Okay, I want to make sure. Okay, doc cam. So 14 electrons. So starting from the bottom, I put 1 electron up, 1 electron down. So there is 2. Electron up, electron down. We're at 4. Up. That's at 7, 8, 9, 10. There's 10 electrons. There's 12 electrons. And there's our 14. So with silicon, that is 1s2, 2s2, 2p6, 3s2, 3p2. Now let's look at where silicon is on the table. It is row 3, second atom in to the non-metal region below carbon. So we have the last energy is 3p, 2 electrons. 2 electrons in to the, as we'll see, p region. Now let's look at calcium. Calcium is 20 electrons. So we're going to keep going from here. So we're at 14 electrons. We have 15, 16, 17, 18, 19, 20. There's 20 electrons. There's calcium. Calcium right here. Calcium 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. What do we note about calcium? Calcium is in the 4th row, second element in the 4th row. It's in the column 2, 2 elements in. We have 2 electrons in the s. Now bromine. Bromine is a little bit harder. Bromine is 35 electrons. So we build our way into the D. 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. So 30, and now finally into the 4p, 1, 32, 33, 34, 35. So I put the last 5 electrons into the 4p. Bromine would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p5. Notice something as we worked our way across from calcium to bromine. What's a new feature of the periodic table that showed up between calcium and bromine that wasn't there for silicon? Suddenly, as we work our way from calcium to bromine, we run into the transition metals. As we worked our way from calcium to bromine, we ran into the 3d orbital. So we had to start filling the 3d orbital. And where is bromine? Bromine is the fifth element in to the non-metal region. It is in column 7A, or column number, I'd like to say 17. So it's 5 elements in. 1, 2, 3, 4, 5. There's a reason behind all this, as we'll see as we look at this in a second. The reason behind all this. Going back to the PowerPoint. Now, here's all re-shown. So if you didn't write down from the document camera, it's right there. But here's an easy way to read the periodic table. We can write these electron configuration without going through this chart. To remember these simple facts about the table. The principal quantum number, so the energy level, is directly dependent on the row. Elements in row 1 are in the principal quantum number of 1. Elements in row 2, as we put electrons in there, those are going to be principal quantum number of 2, so 2s and 2p. Row 3, it has available 3s and 3p. Row 4 is going to have 4s and 3d and 4p to do with. Row 5, row 6, row 7. Now, the column 1 and column 2 are the s orbitals. Remember, only 2 electrons, one up and one down, can fit into the s orbitals. What do we notice about column 1 and column 2? There's only, this weird feature right here, there's only 2 of them there in that weird feature because of how s's fit. P orbitals. There are 3 p orbitals. Each can hold 2 electrons, so there should be 6 electrons in the p. They're all over here. Here, there's 6 elements from 3 to 8. 6 elements from 3 to 8. There's a reason behind that. When we fill this in, all the p, we get to the noble gases. So there's 6 elements here. So all the p's are over here. With E, there are 5 orbitals, each holding 2, so there's 10. If you look at the transition metals, there are 10 transition metals in this feature. And with the F's down here, there is 7 orbitals, so 14. There should be 14 elements in the lanthanides and actinides. Those fit. So S is over here, P is over there, D is the transition metals, and F is here. Now, here's part of the tricky part. Because of the energy designation, D shows up 1 later than you would expect. So when you're dealing with row 4, D is n-1. It's row -1. So when you have the 6th level, you're dealing with 6s and 5d, 6p. When you're dealing with the 4th level, it's 4s, 3d, 4p. The same thing is true for F, except F shows up too late. It's row -2. So row F doesn't show up till the 6th level, but it's dealing with the 4f orbitals. So row 6 would have 4f, 5d, and 6p. Now we're going to fill this working our way across the table. So if I tell you, I want you to do scandium, how would you do scandium? Scandium's right there, 21 electrons after calcium. You could work your way across this table. 1s, there's 2 electrons, 2, 2s, 2, 2p, 6, 3s, 2, 3p, 6, 4s, 2, and then scandium is right here at 3d, 1. I can literally just fill them in, working my way across the table until they're all good. There are a few exceptions to this format in the D and the F subshells. However, I will not test you over the exceptions. I will not test you over the exceptions, but that's why you have things like copper that it's +1 when most of the elements are +2. That's why there's a whole bunch of weird exceptions in the lanthanides and actinides we'll not really worry about. So the S and the P follow the rules really well. So when that labeling, that's called the electron configuration. These electron configurations will help us tell how each element will react because of the periodic trends. When we say lithium will act similar to sodium, which will act similar to potassium, which will act similar to rubidium and cesium, that's because they all have 1 electron in the s orbital. Sure, one of them's in the 1s, one of them's in the 5s, but they all have 1 electron in that s orbital, so they're all going to react similarly. Carbon and silicon act similarly because they all have 2 electrons in the p. So knowing about these orbital designations, these electron configurations will tell us all about how they will react. However, as we get bigger, these electron configurations get bulkier and harder to use because they're like just really top heavy with stuff we don't need. So more often than not, we will look at what's called the valence electrons. The valence electrons come in the valence level, which is usually the highest occupied orbital. It's the highest occupied level. So in the case of calcium, the highest occupied orbital would be in the row 4. In scandium, it would be in the row 4. So calcium was just 4s2. Scandium would have been 4s2, 3d1. Bromine, which is in row 4, would have been 4s2, 3d10, 4p5. The highest filled energy level. The highest filled row is our valence electrons that we need to consider. Everything in the lower levels were the core electrons, electrons that essentially would largely not react. These core electrons are shielded. If you want to peel an onion, you have to first start from the outermost shell. So if you want to peel off electrons, you have to start from the outermost shell before you work your way into the core. Typically, for all main group elements, the number of valence electrons will be equal to the total number of s and p electrons. Going to be a little bit different for the transition metals, but if for bromine, you would have said 4s2, 4p5 are its valence electrons. So it has 7 valence electrons to work with. Remember when we talked about bromine being -1? Well, that's because 8 and 0 are magic numbers here. Adding 1 electron gets it from 7 to 8. Removing 7 electrons would get it to 0. It can range between 0 and 8, with 8 being closer, so -1 being the preferred charge for bromine. But all elements will have the same group, will have the same number of valence electrons. So fluorine has 7, chlorine has 7, bromine has 7, iodine has 7. That's why they all want to be -1. Oxygen would have 6, sulfur has 6, selenium has 6, tellurium has 6. They all typically like to be 2 minus. They all react similarly because they have the same number of valence electrons. Now, we're going to write these valence electrons in what we call the condensed electron configuration, which just emphasizes the valence. We're going to simplify all of the core electrons as a noble gas, the noble gas that comes in the previous row. We're not using the nearest noble gas, we're using the noble gas from the previous row. The way I'm emphasizing this is bromine is in row 4. If you went to the nearest noble gas, you would say krypton, which is one element to the right. We don't want krypton, we want argon, which is 17 electrons sooner, which is element what? Like to say, yeah, something like 18. Something like that. So we want the noble gas from the previous row. So if I was to abbreviate lithium, which would be 1s2, 2s1, we abbreviate it with helium, the noble gas from the previous row, and then just go from there, 2s1. Aluminum, which would normally be 1s2, 2s2, 2p6, 3s2, 3p1, we go to the previous row. Aluminum's on row 3, so we take neon from row 2 and just work our way from neon. So neon, row 3, so starting the S, 3s2. Then I move my way across to aluminum, which is 3p, the first element in. Zirconium, which is in row, like 4, I'd like to say. Is it 4? No, zirconium is in row 5. Zirconium is in row 5. So we start krypton, which is row 4, 5s2, and then the rules for D is row -1. So it's not 5d, it's 4d. Zirconium is 2 electrons in, 4d2. So we're going to do a couple of these on the next slide or so. So first, let's practice the full electron configuration. Let me write these guys down real quick so I have something to work off of. Beryllium, nitrogen, sulfur, zinc, lead. Some of the early ones, you're like, ugh, there's not really a good reason to need the condensed. But some of the later ones, it becomes abundantly clear. So how am I going to do this on a test? I'm not expecting you to memorize this. I'm not expecting you to do the weird Christmas tree thing or whatever. How I do it is I look at a periodic table and I work my way across. So beryllium, right here, element number 4. So the full electron is 1s, 2, 2s, 2. That's the full. If I wanted to go with the condensed, I'd go, okay, this is 2s2, so I'm going to, here's my core, here's my valence. Oh, shoot. Okay. Here's my core, here's my core, here's my valence. So the core, I go up to previous row, helium, I put this in brackets, 2s2. Nitrogen. Nitrogen's right there. Element 7. 1s2, 2s2. I can keep building off beryllium. 2s2. Boom, boom, boom. 2p3. The core is the previous row. Do not make the mistake some people make and try to say, well, it's the last orbital. 2p3 is not the valence. 2s2, 2p3 is valence. Nitrogen has 5 electrons in the valence, not 3. We're not going for which is the last orbital I started to fill. We're going into what row is the last one we started to fill. So row 2 is the last one we started to fill, so 2p3. Once again, not a big savings to use the condensed. It doesn't remove too much. Sulfur. Down here, element 16. Element 16. So 1s2, 2s2, 2p, boom, boom, boom. Neon 6, 3s2, that puts it at magnesium. Then we go 3p, fell asleep. 1, 2, 3, 4, 3p4. And I've hit sulfur, so I stop. Now, what is the core? Well, I filled in the 1s. I completely filled in the 2. So I started to fill the row 3, but I did not completely fill it. So our core is row 1 and 2. So I go up to neon, which is the end of row 2. So neon, 3s2, 3p4. What does this tell me? It tells me that sulfur has 6 valence electrons. It will either want to gain 2 to become 8 or lose 6. In the case of sulfate, it is plus 6. In the case of sulfide, it is minus 2 because of the oxygens. Zinc. Zinc is our first one that's kind of getting heavy now. It's a transition metal. So one as filling in all of sulfurs again, 2s2, 2p6, 3s2, 3p at the very end. Oh, dang it. At the very end, S to argon, 3p6. Starting the next row, 4s2. Now here's the tricky part. We got a D. 3d. Zinc is all the way at the end right here. 3d10. 3d10. The core is everything on the previous row. The valence is everything right here. So we are looking at argon, 4s2, 3d10. There's a reason why zinc wants to lose 2 electrons and only 2 electrons, because it's going to lose these s electrons. It doesn't want to lose any of this 10d because of this, the stability of this. And then lead, way down here. This one is going to be abundantly clear why I want condensed. 1s2, 2s2, 2p6. I'm just copying from the previous one. 3s2, 3p6, 4s2, 3d10. Now working from there. So from zinc, back to row 4. Stop falling asleep. 4p6 gets me to krypton. Row 5, I'm going to start a new row. 5s2, 4d10 gets me to cadmium. 5p6 gets me to xenon. Now we're on the correct row finally. 6s2. Then I'll get into the dang lanthanides and actinides. These get inserted there. So we're going from barium to cerium. You get 4f14 because the lanthanides, actinides, the F is minus 2. So we're jumping from row 6 to row 4 to 4. Then I jump back into the transition metals. 5d10. Then finally lead is on 6p2. Looking at the core is everything before row 6. So the core is element xenon, and they are, guys, 6s2, 4f14, 5d10, 6p2. But largely these guys. So the number of valence electrons that lead actually loses is between 2 and 4. Lead exists as a 2 plus, lead exists as a 4 plus because of that 6s2 and the 6p2. And before you're like, oh my God, he wrote that so fast. I may be working fast, but that's why I say take your time, Have this all shown up, So you can go back to this if you're like, okay, that was a lot. Oh my God, there's a typo. Jeez. Okay, I'll fix that. But that should read 4F and 5D. It's such a goof. Fix that later. Okay. The last thing we will really focus on here is the electron configuration of ions. So how does it change these guys to lose or gain electrons? How does it change these guys to lose or gain electrons? Well, to gain electrons is going to be the easiest. To lose electrons, it's going to be a little bit harder. When we gain electrons, we'll just put the electrons into the highest energy orbital. We're just going to add electrons. So, for example, fluorine down here. When we add electron, it's going to go be 2p5 to 2p6. We've added one electron, it filled up 2p6. Now, because the next electron after 2p6 would have to go into the 3s orbital, fluorine doesn't gain a second electron. It stays fluorine 1 minus. The reasoning behind our charges that we were working on in chapter 2 and chapter 3 has to do with where the electrons would have to go. That's why we kind of do this. Now, magnesium, when we lose a cation, when we lose electrons, here's the hard part. We lose from the P and then the S and then the D in that order. We lose from P and then the S and then the D. So if it has no P electrons, it will lose from the S electrons. If it has no S electrons, it will lose from the D electrons. So it's losing from the highest energy level. So the highest row number, P, and then S, and then D. So for magnesium, magnesium 2 plus loses 2 electrons. The highest energy level is row 3. There's no P, so we lose from the S. So 3s2 goes to 3s0, which can then be unincluded, 3s0. So magnesium 2 plus has the electron configuration of 1s2, 2s2, 2p6. What else has that electron configuration? Well, neon, a noble gas. When it achieves an electron configuration like a noble gas, it becomes incredibly stable, which is why we do this. Fluorine, when it gained electron, is 1s2, 2s2, 2p6, like a noble gas. Notice how both have 10 electrons. Even though they have a different number of protons, they both have 10 electrons. This is known as being isoelectronic. Just like an isosceles triangle has these 2 sides that are equal, isoelectronic means they have the same number of electrons. You have 2 elements that have the same number of electrons. But we will go ahead and stop there. We're going to talk briefly about quantum numbers and maybe go over some Achieve homework on Wednesday. before starting the next chapter. But that is where we will stop. Oh, we are essentially done with this chapter.